in Unit 3, we discussed about the force and different types of forces. And we also saw how different types of forces can act on the same object and how to deal with the forces to find the net force acting on any object. Now, in this unit, Unit 4, we are going to see the consequences of the forces. So, the consequence of a force or a net force could be in work done, energy and power. So, in this unit, we are going to see the interrelationship between force, work done, energy and power. So, now what is work done? So, to begin with, let us deal in detail with the work or the work done, and then we will discuss in detail the other two topics, energy and power. So, work is the term which we casually use in our everyday life, and the students feel studying their lessons itself is a work, and women think cooking food is a work and cleaning the floor is a work. And this is how we have been using this word work very casually. But actually, in physics, it has a definite definition and the prescription to deal with work. So, how to define work as a physical quantity in this unit 4? When a force acts on the object, if it displaces the object, then the work is said to be done by the force. When a force acts on an object, displaces it, then work is said to be done by the force. Since it's a fundamental definition, let me just write it on the board for your clarity. Work is said to be done by the force when it displaces the object on which it acts. Work is said to be done by the force. So, force is involved here, displacement is involved here, and therefore, the work done or the work has some connection with the force and the displacement. So, this is how we define work. And what about energy? So, when you do some work, you need energy, and therefore, we can say the ability to do work is energy. So, the next definition I would just write here, energy is the ability to do work. And therefore, we can say the energy and work are equivalent to each other. So, force displaces and therefore, work is done. For that work done, energy is required, and therefore, we can say energy and work are equivalent to each other. We can say they are equivalent. So, when we say equivalent, both of them have the same dimension. So, now I want to go back and see this. I said work, force and displacement are related. So, shall we write a formula connecting these three as the equation for work done and discuss the impact of that work done, and then we will move on to energy. from the definition of work done, we said 3 parameters are involved: work, force and displacement. Work is represented by this letter W, force by F and the displacement dr. So, how these 3 are related with this equation? The work done on an object is the scalar product of the force and the displacement. So, now if you see, this is a vector quantity and displacement is a vector quantity. Now, I have taken a scalar product because it is a dot product. So, the dot product of 2 vectors would result in a scalar, as we have discussed in unit 2, and therefore, the work done is a scalar quantity. So, the scalar quantity will have only the magnitude and it will not have any direction. So, work done will not have any direction. And now, let us go back to this equation. So, when we analyze this equation, we see F work done and the displacement. So, individually they have their own units. So, combining these two, the unit for work done, the unit for W is Newton meter or joule. It is also represented by the letter capital J. The dimension of work done is m L square T inverse 2. We have already done this in the dimension analysis of the first unit, where m corresponds to the mass and L for the length or the distance and T for the time. So, this is how we write the dimension, and later on we will be able to realize the dimension for energy is also the same because they are equivalent to each other. So, now look at this particular equation. So, let me call this equation as 1. So, the dot product of 2 vectors are already discussed in our vector analysis. Suppose you have a vector A and vector B which are taken as scalar product. So, when you take a scalar product of the 2 vectors, this is how we write AB cos theta. Similarly, we can apply the same dot product rule here and write the work done to be equal to F dr cos theta. So, this is also another way of looking at this equation, but it is very useful in understanding its significance, especially in problem solving. This is more general way of writing it. So, now look at this equation 2. When you look at this equation 2, we understand this magnitude of work done depends on the magnitude of force, the displacement it causes, and also the angle theta. So, what is this angle theta? Theta is the angle between the direction of the force, because only 2 things are involved: force, which is in a particular direction, and it causes a displacement which is also in another direction. And therefore, it should be the angle between the direction, or I can say directions of the force and the displacement. And therefore, the angle theta also decides the magnitude of the work done. So, how does it go? So, let me just demonstrate with a simple example here, and then we will come back to the impact of it. So, this is a simple demonstration to understand the work done equation. So, now this is the object, and this object, when a force is applied on it, would start moving. So, I can do it 2 ways. One way is to push it. So when I push this object, I give the force by pushing it towards my right. So this is the direction of the force. Now carefully watch, I am just giving a push and the object is moving in this direction, and therefore this is the direction of the force and this is the direction of the displacement, and therefore both are in the same direction. So in this case, the angle between the two would be 0. Another way of looking at it is to pull it. So when I try to pull this particular object, I'm just pulling it through a string like this. So pulling is also giving a force where the force is trying to pull the object towards my right, and therefore the direction of the force is this. And what about the displacement? The displacement, as it pulls towards my right, the object is also moving towards my right. So in this particular case, the angle between the direction of motion, that is this, the pink one, this is the direction of motion, and this is the direction of the force, that is from here to here, and both are in the same direction. Here again, the angle between the direction of the force and the direction of displacement is 0. And now carefully watch, I would like to show you different situations. The first situation, as we have already said, 0. And now is it possible for me to slightly give a force like this? Suppose an object is going to be pulled by this string, which is not horizontal like this, but it is inclined slightly. So when it is inclined slightly, still it can pull the object. Now see, the object is moving in this direction, but the force is given in this direction. So this is the direction of the force, and this is the direction of motion of the object. And now the theta would be the angle between this direction, that is the direction of displacement, and this is the direction of the force, and therefore the angle between this pen, which is direction of displacement, and the string, which is the direction of the force, would be theta. Now it is possible for me to change this angle. Now I am changing the angle a little more than that, and still I can pull it, and then this can be another angle. So now what I have done, the direction of displacement and the direction of the force is 90 degrees. When it is 90 degrees, when the force is pulling it, it is impossible for the object to move in the right direction because the pull is upward, and no longer this force can make the object move in this direction. And therefore, we are able to see when both coincide, angle is 0, and when the angle shifts, magnitude of the work done will be changing. When the angle comes to 90, the work done is almost 0. So this is what is the simple definition or simple demonstration. Now let me just apply it on the board and see the consequences.